Hello, I am a postdoctoral research fellow at Seoul National University, and my name is Byungchul Kim. This presentation is for introducing my researches conducted in my PhD degree and my postdoc period. This presentation only explains our contents briefly, so please look for my personal homepage for more details. You can access the site using a QR code in this slide. Before explaining my research, I would like to point out an important point when developing the wearable robots. So let's imagine we are developing a wearable chair for non-disabled people. Then this device can be developed with the goal of reducing EMG levels, where EMG can be thought as an indicator of muscle activity. Or you can think of how many postures the device can support. However, our experience developing wearable robots has shown that other factors related to comfort are just as important as factors related to functionality. In this presentation, I would refer the factor related to the user convenience as a usability. In hand wearable robot researches, there is also robot performance related to functionality and usability. As we all know, hands play a variety of roles in our daily life in a compact size. Therefore, it is difficult to satisfy both factors related to the functionality and usability. So for instance, when we design the hand wearable robots using many motors, then it will increase the robot versatility, but it will also make the robot complex. On the other hand, if we use less actuators, then we cannot assist various postures, but the robot can be simple. So I wanted to find the optimal point between these two factors. So my researches are all related to these trade-off issues. So I'm going to talk about existing trade-off issues related to the hand wearable robots. And then I'm going to present about how I designed the robot to solve these issues. So the first issue is related to the number of actuators, as I explained in the previous slides. So when we use lots of actuators, then the robot can assist dexterous motions, but the system becomes complicated. In contrast, if we use less actuators, then we can construct the robot simpler. However, it is obvious that the robot will have limited functions. For the issues related to the number of actuators, some researchers have proposed a tendon-driven under-actuation mechanism. Interestingly, using this mechanism not only enabled to reduce the number of actuators, but also made interesting motion pattern. As the video shows, when we use a tendon-driven under-actuation mechanism, then even one finger is blocked by the external environment. The other finger can continue their motion. This motion pattern is usually named as the adaptability. Since this adaptable motion stabilizes the grasp performance by increasing the contact points, numerous researchers have utilized TDUM to deal with the trade-off issue related to the actuator number. However, the use of this mechanism also causes trade-off between the functionality and usability. So when we use under-actuation mechanism, then we can make adaptive motion with less actuators. However, this mechanism requires complicated tendon routing and causes high frictional force. In addition, Because not all joints can be individually controlled, it is not always possible to perform the desired tasks. On the other hand, when we do not use this mechanism, then we must use numerous actuators, so the system can be complicated. However, when we do not use this mechanism, then we can contour each joint more accurately. Also, the tendon routing becomes more simpler so that it is more easy to fabricate the robot. The third issue is related to the compliance of the robot body. So for instance, if we use rigid component as a body of the wearable robot, then it is possible to transmit the force more accurately. However, when we use rigid component, then we have to align the robot joint with the user's finger joint, meaning that we have to design some mechanism that aligns user joints and the robot joints. For this reason, the rigid wearable robots becomes bulky and complicated. The other researchers have designed the wearable robot with soft component such as garment or silicone to solve this issue. By using the soft components, we can make the robot simple and compact because we don't need any joint alignment mechanism. However, since the soft components elongates easily, the force transmission can be inaccurate as shown in the video at the left side of the slide. And the last trade-off between the usability and functionality is related to a method of estimating the human state. So in the wearable robot studies, since controlling the robot requires human state, numerous researchers have tried to measure the human state. So in hand wearable robot studies, the researchers tried to estimate the joint angle. Then by using this joint angle, they tried to make various hand postures by controlling the robot system. So in hand wearable robot studies, they used some sensors at the glove. I mean that most common method to measure the human state was to attach sensors at the glove. However, in this case, the glove can be bulky and complicated. Also, if we use rigid PCB circuit, then it harms the softness of the robot body. However, it is obvious that we can measure the human state accurately. So these are the advantages and disadvantages. So for this reason, some of researchers have tried to remove the sensors at the glove part to make the robot simple and compact. However, in this case, we should estimate the joint angle by using only the motor position and motor torque. Since there exists lots of uncertainties in the robot system, the estimated result was not that accurate. Also, due to this reason, it was not possible to control the robot using these estimated joints. So my researches are all related to the methods of solving the trade-off between the robot functionality and usability that explained in my previous slides. So first of all, for the trade-off related to the under-actuation mechanism, I have designed a tendon-driven linear actuator called slider tendon linear actuator. This actuator was developed to include several mechanisms that improve the robot performance. By using this actuator, it was possible to simplify the glove part, even using the under-actuation mechanism. It is because this under-actuation mechanism was involved in the actuator, not in the wearing part, so that the actuator made the end effector compact. The second issue is related to the number of actuators. So for this issue, I first obtained important motions according to the previous biomechanics studies. In assisting the hand, the thumb motion was important. So I aimed to drive the minimum number of actuators required to assist the thumb, index, and middle finger. And by simulating the hand motions using the MATLAB, I found that using 4 actuators was sufficient for the robot to assist 3 fingers. For the robot compliance issue, I aimed to use both rigid and soft materials. By designing the entire robot body with soft garment, it was possible to make the robot compact by eliminating the joint alignment mechanism. Also, by using the metal shell, I aimed to make the precise force transmission. And this hybrid design not only increased the robot functions by using these 2 components, but also made it easier to fabricate the robot. And lastly, I aimed to estimate the joint angle of the wearer using the motor torque and displacement. Since there exists several uncertainties when I estimate the joint angle using the model-based method, as I explained in the previous slides, I used data-driven method to estimate the joint angle. By estimating the joint angle without any sensors at the glove, it was possible to sustain the robot system compact and simple by using this method. As a result, I have designed a robot named Exoglove Shell by considering these 4 trade-offs between robot functionality and usability. So by considering hand biomechanics, the robot is designed to assist the thumb, index, and middle finger. Also, by simulating the hand kinematics, I obtained that using 4 actuators is sufficient for the target application. Also, to use under-actuation mechanism without increasing the robot complexity, I have used the slider tendon linear actuator as I explained in the previous slides. Lastly, the robot has a hybrid design of rigid and soft component. So by doing so, it was possible to transmit the force accurately without making the robot bulky and complicated. And detailed explanation about these robot components is explained in my personal homepage. So please look for my homepage for more detailed explanation. And if you have any questions, then please contact me in my by mailing to me. Thank you.